Industry skills, practical knowledge, real-world impact. This is Simple Gyan.
A fully loaded truck is moving on a broken road. Thousands of kilograms of load are pressing downward. The axle is receiving shock after shock. Every pothole is trying to bend the chassis and destroy the vehicle. But between the road and the body, one component silently does its job. It has no electronics, no hydraulics, and no computers. Just a few curved metal strips, stacked together. This is the leaf spring. It looks simple, but it is an engineering powerhouse. This simple part carries massive loads and has survived from horse carriages to modern trucks. How can curved steel carry tons without breaking? Today we will decode the complete engineering of leaf springs, their history, science, design, and why heavy vehicles still trust this technology. Before modern highways, roads were stone paths and muddy tracks. Sitting in a wooden carriage without suspension was a nightmare. Every road impact went straight to the passengers. This problem forced craftsmen to create a flexible connection between the wheel and the body. Leaf springs are among the oldest suspension systems. Used in carriages long before the car, they evolved from simple laminated strips. In 1804, Obadiah Elliott patented an elliptical arrangement. This wasn't just a comfort upgrade, it was a transportation revolution. Once loads moved smoothly, travel became faster and cargo damage reduced. A design born for horse carriages became a pillar of history. What exactly is a leaf spring? It is made from long, narrow, curved plates called leaves, usually crafted from high-strength spring steel. They are stacked one above another. The longest is the master leaf. Shorter leaves sit below it to provide graduated support. A center bolt holds the pack together, while clamps keep the leaves aligned. The ends connect to the vehicle frame through eye bushes. In simple words, it's a flexible steel beam that bends under load and returns to its original shape when the load is removed. The beauty of leaf springs is their multitasking. They support the vertical load, help locate the axle, and provide natural damping. To understand how it carries tons, imagine a steel ruler. If you press the middle while holding the ends, it stores energy in bending. During bending, the top and bottom surfaces experience different stresses, tension on one side and compression on the other. The curved shape, or camber, is critical. When load increases, the camber reduces, allowing the spring to absorb energy gradually. The massive load is distributed through the entire length of the spring. It spreads the force rather than fighting it at a single point. Why not use one thick steel plate? A single thick plate would be too stiff, creating high stress concentrations and a very harsh ride. Multiple thinner plates create progressive behavior. As the load increases, shorter leaves come into action, making the spring stiffer as needed. As they bend, the leaves slide. This sliding creates interleaf friction, which acts like a small damping force to reduce bouncing. Friction is both useful and problematic. Modern packs use liners and special coatings to reduce noise while keeping the movement controlled. Let's look at the master leaf. Its ends are rolled into eyes which connect directly to the vehicle frame through specialized bushes. The center bolt keeps the stack aligned while U-bolts clamp the axle. If these U-bolts loosen, the axle can shift, a major risk. The shackle is the most clever part. It allows the spring to grow longer as it flattens, letting the suspension breathe without binding. The leaf spring is basically an energy storage device. Road impact energy is stored as strain energy in the metal, then released. This is why we need shock absorbers. The spring stores the energy, but the damper dissipates it, preventing endless bouncing after a hit. A spring fails from millions of small cycles. Every pothole and speed breaker adds to the fatigue that designers must carefully calculate. In engineering, the surface is key. Shot peening creates compressive stress on the surface, helping the metal resist the start of fatigue cracks. Why do heavy vehicles still use this design? Because they are simple, strong, and can handle massive torque and braking forces. Leaf springs spread the load over a wider area of the chassis. Coil springs concentrate that force into a single high-stress point. Let's trace the path of 10 tons. From the cargo to the chassis, through the hangars into the springs, and finally the road. When a truck hits a pothole, the axle pushes up. The spring bends rapidly, delaying and reducing the impact on the body. This is suspension. But overloading is the enemy. It doesn't just damage the spring, it cracks the chassis and turns a brilliant design into a safety risk. Watch for the signs: uneven height, broken leaves, or persistent squeak. In maintenance, these simple parts should never be ignored. Not all leaf springs are the same. From the common semi-elliptic in trucks to historical full elliptic designs, the variety is vast. Some modern cars use transverse leaf springs, running across the vehicle instead of along it, proving the design is still evolving. Manufacturing is a precise science. The steel must be heated, formed, and then carefully heat-treated for the perfect balance. Too hard and it becomes brittle, too soft and it permanently bends. Quenching and tempering ensure the material can handle the load. The future is composite. Engineers are using glass fiber reinforced polymers to slash weight and improve fuel efficiency. Composite springs can save significant weight in commercial vehicles. Less weight means more payload and lower emissions. But composites bring challenges in cost and damage inspection. Steel remains the king for easy, low-cost maintenance in heavy trucks. Now for some interesting facts. Did you know leaf springs are one of the few parts that can act as both a spring and a locator? The friction between leaves provides natural damping. Even without shocks, a leaf spring tries to control its own movement. A truck leaf spring doesn't only carry weight, it also handles braking forces, driving torque, side loads, and road shocks all at once. Leaf springs are used because they are practical. In engineering, the best solution is often the one that is most reliable and repairable. An overloaded truck overloads everything: the engine, tires, brakes, and steering. The suspension is just the first line of defense. A small worn bush in a spring eye can disturb axle alignment and destroy your tires. Small parts create big consequences. Many technologies become obsolete, but leaf springs have survived. Why? Because the best engineering solves problems reliably. Leaf springs are old, but not outdated. They are simple, strong, repairable, and economical for heavy loads. They just work. In cars, comfort is top priority, but in trucks, load carrying and durability win. That is where leaf springs truly shine. They are not glamorous or high-tech in appearance, but they are brutally effective at what they do, day in and day out. A leaf spring is a perfect example of practical engineering. It converts simple steel bending into massive load-carrying strength. It converts material elasticity into reliable suspension movement, a simple geometry perfected over centuries of real-world use. Next time you see a loaded truck, look near the rear axle. You'll see those curved steel plates carrying tons of weight. It is absorbing shocks, controlling movement, and protecting the chassis, all while staying completely silent and invisible to most. From horse carriages to modern highways, from steel to composites, the leaf spring has proved a powerful engineering lesson. Engineering doesn't need to be complicated to be brilliant. Sometimes the strongest solution is a simple idea, perfected over time. This is the story of the leaf spring, an old invention that still carries the weight of the modern world. It is the heart of transportation. If you enjoyed this engineering breakdown, subscribe to Simple Guyane for more deep dives into the hidden systems that power our world. Thanks for watching. We'll see you in the next deep dive into the machines that make our lives possible.